This is the key for Exam 1 from spring of 2013. The first thing we're asked to do is rank these sets in terms of acidity of the OH hydrogen. 1 is the most acidic. So in the case of the first set A, we're basically looking at where the chlorine is on this 4-carbon chain. Here the chlorine is right next to the OH, here it's very far away from the OH, and here it's in the middle. And so that's going to give us different variations on induction, which causes the OH to be more or less acidic. So the closer the chlorine is, the better the induction. So we would number them this way. For set B, we have a bunch of phenols that have some substitution or not substitution, and we have groups that are halogens in the meta and para position, and we have just phenol by itself. So we can assume that the phenol by itself is going to be less acidic than the two compounds that have some electron withdrawing groups attached. The closer the electron withdrawing group to the phenol, the more effect it will have. So this chlorine is a little bit closer to the OH. That should have more of an effect on the acidity of this hydrogen than the fluorine, which is a little further away on the para position. So this OH should be a little less acidic than this OH, and that gives us our numbering. By coincidence, it matches the top set. Okay, on to part 2. We're asked to provide names for 2 of these following compounds. The first question, the first one, involves a alcohol, so we're going to start numbering nearest the alcohol. That gives us 2 non-enol, and we have 2 stereocenters on carbon 4 and on carbon 2. So if we look at carbon 2, the priorities are as follows, and that gives us an S, so we would have 2S. And at carbon 4, let's change colors. The priorities at carbon 4 would be the chain bearing the OH, then the longer chain, and the shorter chain. And again, that is counterclockwise, so we also have S, so 4S. And then we can start writing our name here. And we have 2 non-enol, and we have at the 4 position an ethyl. So we would have just 4-ethyl 2 non-enol. And of course you could write 4-ethyl non and 2-ol if you wanted to as well. Now, naming aromatic rings, as we learned in class, we can name them as potentially a substituted common name. So methyl on a benzene ring is toluene, so we could name this as a substituted toluene. That means we would start our numbering right here. Or we could simply name it as a substituted benzene ring with 3 substituents. In that case, we start our numbering at whatever position will allow us to have the smallest numbers possible. And again, that would be right here because we could get 1, 2, 4. If we started here, we would go 1, 3, 4, which is obviously bigger than 1, 2, 4. And of course, we certainly don't want to number around the other direction. So let's go ahead and start that numbering. If I name it as a substituted toluene, I have 2 bromo 4 methoxy toluene. If I name it as a substituted benzene, I have basically the same thing, 2 bromo 4 methoxy 1 methyl benzene. And for the second one, we have priority now with the OH, so that will dictate the numbering. We number the OH as number 1 and then number in either direction to minimize the numbers. Or we could label this as a substituted phenol with the OH on the benzene ring being a phenol, and that would again dictate the numbering. It's going to give us the same numbering scheme, so we should number here 1, 2, 3, 4, 5. And that's different from, let's number the other direction just to see, 1, 2, 3, 4, 5, 6. So I get 1, 2, 5 in my green numbers, or 1, 3, 6 in the red numbers. So you can see that the green numbers are the better way to number this. So let's go ahead and name this. A substituted phenol would be 5-ethyl 2-methyl phenol. And if we named it as a substituted benzene ring, I think we'd use hydroxy But really, I don't think I like that name. So I'm going to say that this is probably the best way to name it as a substituted phenol, because we really don't talk about hydroxybenzene very much, because that is exactly what phenol is. So I think that's the best way to name this compound. Let's move on to question 3. All right, for each pair of reactions, we need to circle the reaction which would have the fastest rate. So we're going to look at probably, well, the difference here is that there's a chlorine or an OH substituent. And so we'll look for the most strongly activating substituent, and that's going to be the OH. That is a strong activator, and so we would circle this side. That's going to have the fastest rate in bromination. For part B, we've got a nitro group on both rings, but we have a hydroxy or a OH group on the ring on the right side. And so that's certainly going to be a more activated ring, because that has the strong activator again, so we'll circle the right side. And then for part C, we've got toluene with a methyl group versus acetophenone with a ketone group. So an electron withdrawing group versus a moderate activator or a weak activator. This is a moderate deactivator, and so we'll circle toluene because it is the most activated ring in this case. Question 4, propose a reasonable product for these reactions. So the first thing we want to do is look at this alcohol, TMS chloride, and pyridine. This is a way to protect alcohols, so really the product is simply OTMS. The pyridine is going to soak up the H, and the Cl makes HCl gas, or HCl the acid. The pyridine soaks that up. Pyridine is just a sacrificial base in this case. Second one is this methylated phenol is going to get nitrated, and so we're going to choose the location of the nitro group based on the strongest activator here. So they're both activators. The OH is a stronger activator. It is an ortho-para director. Here's ortho, here's para. We can't put it on para, so we're going to draw the nitro in the ortho position relative to the phenol. Okay, part C, toluene plus KMnO4, that's a strong oxidizer. We have a benzylic position, so we're going to oxidize that all the way to the carboxylic acid. Part D, an ester and a ketone with NABH4 in ethanol. Remember that NABH4 does not affect esters, so we should draw that remaining as an ester and reduce just the ketone to the secondary alcohol. Part E, we've got a dibromo and a ketone, and we're going to do NaOH followed up with acid workup. So this is probably going to be a nucleophilic aromatic substitution because we have good leaving groups and we have an electron withdrawing group that can help this ring become more receptive towards a nucleophile. And so we need to decide which of these electron withdrawing groups will be substituted. It's going to be the one in the ortho or the para position to the electron withdrawing group. You can draw some resonance to show why, but that means that this bromine gets substituted with OH. This one is unaffected. And we can think about the electron withdrawing groups. This resonance pattern is available to us. If we have the OH attack at that top bromine. So if you attack that top bromine, push some arrows, you should be able to draw that resonance pattern. Part F, we have a nitro group with zinc and HCl. We're going to reduce that nitro group to the amine. So this is a way to make amines. And this is the only way that we've learned at this point in the semester. Part G is simply a Grignard addition to a ketone. And we know that acid workup, after acid workup, we end up with the tertiary alcohol. And lastly, we have a primary alcohol plus the strong oxidizing agent, H2CrO4. So we're going to end up with not just the aldehyde, but the carboxylic acid. So that's going to oxidize all the way to the carboxylic acid. Question 5. Write a reasonable arrow pushing mechanism, including all relevant resonance structures for the following reaction. So here we have an alkyl chloride with aluminum trichloride. So this is going to be a Friedel-Crafts alkylation. We've got a ring that's activated with a weakly activating group, methyl, and a strongly activating group, NH2. And so what we're going to do is substitute probably on the para position of the NH2. And so the first thing to do is to make the electrophile. And I'm not going to draw this arrow here because that would show a primary cation being formed. So I'm going to leave it as the activated alkyl halide, and then I'm going to draw some arrows that then allow attack at that primary position. And I'm going to draw the intermediate now. That's the cation there, and then I can draw some resonance structures as directed by the question. I'm going to skip ahead here. Okay, so I have my 4 resonance structures, including this one, which is the most important structure. It shows why the NH2 is an ortho-para director and why it is a strongly activating group. And so I can take the final resonance structure and find, let's see, I'll use my aluminum trichloride or tetrachloride anion right now. I can use this AlCl bond, remove this H, drop the electrons down and produce the pi bond, reforming the aromatic ring, and with our new ethyl substituent on it. Now I should say that after I wrote this question, realize that the NH2 here is a very good nucleophile. It is also possibly going to react with the Lewis acid, or it could react in a SN2 type reaction with the ethyl chloride to put an ethyl group on this nitrogen. So reality is that we probably would not get this product here, but since it was shown here as a product, we can at least propose a mechanism on how to produce it. But if you were going to be asked to make this product in a synthetic route, we probably don't want to have this NH2 group in the presence of ethyl chloride or aluminum trichloride. Question 6. Here are some choices of reactions. Choose the best reaction and tell me why. So let's look at A. Looks like we're going to take phenol and add a bunch of substituents to it. And so we have, of course, the OH is going to add ortho-para. It is the strongest activating group, so we'd expect to fill up the 2 ortho positions, which is what happens. So we've added a chlorine to one ortho position, SO3H to the other ortho position. We've got that happening in both reactions, so really no change there. It just looks like the differences are in the order of addition. Do we add the chlorine first and then the H2SO4, or should we add the H2SO4 and then the chlorine? And the reality is both will probably get to the product. So that's not really the difference that we're looking for here. If we, let's see, look at the activating qualities of the 2 groups, SO3H is probably a moderate activator, a deactivator, sorry. Remember there are SO double bonds coming off of the sulfur, so that's going to be an electron withdrawing group. The chlorine, of course, is by induction an electron withdrawing group. However, we know that it has a lone pair, that it can donate, so that it is an ortho-para director, but a weak deactivator. And so if we're going to just think about this from which one should go on first, would we put the strong deactivator on first or the weak deactivator? It's probably better to put the weak deactivator on first, because that makes the second step not as difficult as if we put the strong deactivator on first. We've deactivated our ring further and then try to put the chlorine on. So I think that the top choice is the best one, and this choice and really I think it's as simple as that. The bottom choice would result in a slower, more difficult second step because we are deactivating the ring strongly with our SO3H group. Let's look at B. We're taking the OH to a bromine, and looks like we're undergoing inversion. There is no plus minus here, so we can assume we're making one stereocenter. And we just have 2 choices, PBr3 or HBr. And we learned that PBr3 will invert the stereochemistry as it takes an OH to a bromine. So that top one seems pretty reasonable. What's wrong with HBr? Well, that's going to be sort of a probably SN1 type mechanism, because we'll protonate the OH, lose it as a decent leaving group as water, and then the bromine could come in and attack the cation. So this likely will be racemic mixture. And so we probably should choose the top so that we can ensure we get just the one stereocenter. All right, on to part C. Let's see, we're installing two groups again, it looks like, the NO2 and the methyl, and looks like the only difference is the order of addition. Should we put the NO2 on first, then the methyl, or should we put the methyl, then the NO2? Well, it really comes down to the fact that the NO2 is a meta-director, the methyl is an ortho-para director, and these two substituents have a para relationship. So we should definitely put on the methyl group first, which would mean the bottom reaction is best. So the top reaction would result in, let's see, NO2 and a methyl in the meta position. And in fact, the Friedel-Crafts alkylation probably won't occur on strongly deactivating rings. So this reaction may not even occur. That would be also a good reason to argue against it. You might get no reaction at all once you've nitrated the ring. All right, question 7. Circle those you expect to be aromatic, and if you don't circle them, tell me why. So we're looking for 4n plus 2 pi electrons, and we're looking for a ring, and we're looking for p orbitals all around that ring, and we're looking for planarity. So let's investigate these. Here we have, this is pyridinium cation. This is just pyridine with an extra hydrogen. It does have the 3 pi bonds, which gives us 6, which is equal to 4n plus 2. They're in a ring, they're planar, they're all p orbitals, so I'd say that's definitely going to be aromatic. This is cyclopropene anion, and that is in a ring. We could say there are p orbitals all around the ring, but if I count the 2 electrons with the anion and the 2 in the pi bond, I get 4 electrons. That is not 6 or 2. 4 does not equal 4n plus 2, so I'm not going to circle this one. This is actually anti-aromatic because it satisfies all the requirements except for the count of electrons. It is actually, it is 4n electrons. So this makes this anti-aromatic, very unstable, highly unlikely that it would form. Here's a cation. Looks like it's cyclohexadiene plus the cation. The problem here is that this carbon is a CH2, which means it does not have a p orbital, and so no p orbital. That makes it not just non-aromatic. It's not bad. It's not anti-aromatic like this is, because it has a ring with p orbitals all around it. It's just not aromatic. So this is not aromatic. It's totally fine molecule, just not aromatic. And here we have an cyclooctane ring with 3 pi bonds and 2 cations in it. And if we assume it's planar, there are p orbitals all around it, and there are 4n plus 2 pi electrons. So that one is aromatic because it satisfies all of the criteria. Okay, question 8. Provide a synthesis of one of these molecules, starting with the starting material. So let's look at the one with benzene. We've got a meta-director, we've got an ortho-para director, and we've got an ortho-para director in the chlorine. So if I were to look at the nitro group, there is nothing meta to the nitro group. So we did not use the nitro group to install anything. And that sort of makes sense because the nitro group likely would be one of the later additions because it's going to deactivate the ring. If we look at the alkyl group, that is, it's got a ortho nitro group and it's got a meta chlorine. So it's possible we used it, but we'd have to, I don't know, put the chlorine on some other time. If we look at the chlorine, it's meta to the alkyl group and para to the nitro group. So I think we are going to have to find a way to install a substituent, use it as a directing group, then change its directing ability and use it again to put the second group on. And I think that's going to be this alkyl group, because remember, we cannot just put on a 3-carbon alkyl chain like this. It would rearrange. So most likely we started with a ketone in this position. So let's look at that. What if we had a ketone that we installed first? And now that's a meta-director. We can install a chlorine in the meta position. And now we can reduce that ketone to the alkane, turning that into a moderately activating ortho-para director, which would be used then to install the nitro group. And now we need to figure out how to reduce that, and that's going to be the Clemmensen reduction. So that's zinc, mercury, and HCl as our proton source. And so that would be the nice 4-step synthesis to make this tri-substituted benzene ring. Let's look at the second synthesis. We're given a primary alcohol. I think that it's pretty obvious that those carbons that I circled are the carbons that I started with, and thus this carbon continues to have a functional group, and at some point we turn it into a chlorine. Now we know how to add chlorines from alkenes or from alcohols. Since we start with an alcohol, it's a reasonable assumption to say that maybe the last step is, with an alcohol in this position, we turn it into a chlorine. A couple ways to turn alcohols into chlorine. I'm going to use SOCl2. And so now what I've done, I've gone backwards 1 step. My final step is SOCl2 plus the alcohol gives me the chlorine. And now I can look at my primary alcohol, and I need to convert it to a secondary alcohol and add this carbon group, making this carbon-carbon bond. And I know how to add carbon groups via Grignard reactions, and a Grignard reaction requires a carbonyl. So if I could turn this into a carbonyl, I could add this cyclohexane ring as a Grignard. That would give me probably, depending on what I start with, a secondary alcohol that I could then react with SOCl2. So I think that I can turn this into a carbonyl via PCC, and that's a good reaction or reagent to react with a Grignard. I have an aldehyde. I can then use a Grignard that is shaped appropriately. First step. Second step is acidic workup to protonate my newly formed alkoxide, and then I get my secondary alcohol that can be changed into a secondary chloride. So I think we have a 3-step sequence here that gets me from my primary alcohol to my secondary chloride. Last question. Let's fill in the intermediates here for the following roadmap problem, and it's going to help us learn how to add an aldehyde to an aromatic ring. So let me zoom in a little bit here. The first step is toluene plus an acyl chloride and AlCl3. Toluene is an ortho-para director, and we know that the aldehyde group is added para to the methyl group, so we might as well add our ketone to the para position. Zinc, mercury, and HCl is the Clemmensen reduction. We make ethyl methyl benzene, and let's just confirm that these reagents up here will also give us ethyl methyl benzene, and I think that's probably true, so we're on the right track. Then NBS is going to brominate, and we will brominate at the position that's most stable to a radical, and that's going to be the secondary benzylic position, not the methyl benzylic position. So either of these positions could be brominated with NBS. They are both benzylic positions. But remember that we're forming a radical before the bromine adds, and so a radical will be more stable here than it will be here, simply because it's more substituted. So we're going to turn a create a secondary bromide here, and now we have strong base, which is not a good nucleophile. And that gets us to that alkene, so we're going to do an E2 elimination with this step here. Gets us to this alkene, and of course ozone and DMS will cleave this alkene, leaving us with an aldehyde. Lastly, the bonus, we want to draw an arrow pushing notation to draw a mechanism for this reaction. So it looks like we're putting on this 5-carbon group on an aromatic ring. I have 5 carbons here, so it's probably that group. How do I make that into a good electrophile? Because this is probably going to be electrophilic aromatic substitution. Well, I would protonate the alkene with my strong acid. And that would give me this secondary cation, which would probably rearrange to form the tertiary cation. And I know that I need that because I'm making a new bond to the tertiary position on that 5-carbon chain. So now I have a good electrophile. I've got benzene. I'm going to attack with benzene, producing this structure. And I still have this H, and really the only thing that I could use to grab the H would be either HSO4 minus, which I don't really like much because this is a very weak base, because it's the conjugate base of a very strong acid. But I could also use some of my starting material. I know that this acts as a base in the reaction, so why not use another alkene to remove the extra H. That alkene will get protonated. It can start the mechanism all over again. My drawing here gets deprotonated to produce the desired product.